Let's look at how to measure the distribution and its shape. If you remember from our first session, we looked at several graphs showing the distribution of data, and some of them are skewed, i.e., not everything is symmetric. Sometimes data will be skewed to the right or skewed to the left. There is a formula for calculating the skewness, and it's usually easily calculated by statistical software. We will not focus on calculating here, but let's do a review of what skewness means. So look at this graph. Look at the distribution. It's symmetric. The right side looks exactly the same as the left side. Hence, we say that its skewness is 0. As we will later see in the case of the normal distribution, this means that the mean and the median are equal. Now consider this. There is a tail on the left, and it's moderately skewed left, i.e. there's a tail, but it's not all that long. In this case, when it's skewed to the left, we say that the skewness is negative, and the mean will usually be less than the median. Now look at this. There is a tail on the right, hence it's moderately skewed right. In this case, the skewness is positive. Look at this. It has a really long tail, hence it's highly skewed right, and the skewness is positive and usually has a value above 1. So again, let's look at the monthly apartment rent data. They've arranged it in ascending order. Let's look at the frequency distribution. How would you describe the skewness? To the right or to the left? Well, as you can see, there's a tail on the right, hence it's moderately skewed right. And as you will see, the skewness as measured is 0.92. It's high, but not above 1. Now remember, we said that the measure of location is the mean, and the mean indicates to us where the center is. The concept of the z-score, whose formula is given here, and which can easily be calculated by, for example, Excel. Well, the z-score gives us the following information. It tells us the relative location, because if the mean tells us where the center is, then the z-score will tell us for a certain value how far away is it, or how near is it to the center, which is the sample mean. Hence, if a value is exactly equal to the mean, then it will have a z-score of 0, because it's equal. And if a value is greater than the sample mean, then it will have a z-score that is positive, or greater than 0. And if a value is less than the sample mean, then it will have a z-score less than 0. So again, look at the apartment rent data. What we do is for each value, we calculate its z-score. So take for instance 425. How do we get its z-score? Take 425, subtract the mean from it, which is 490.8, and divide by the standard deviation, 54.74. It gives you a z-score of minus 1.20. Why is the z-score negative for a value of 425? It's negative because it is less than the mean. And remember, values that are less than the mean will have z-scores greater than, will have z-scores less than 0. So as you will see, look at this lower right hand corner. Let's go back to that. That's the data for 615. Since 615 is greater than the mean, we predict that its z-score will be positive. And indeed it is. It's 2.27. And what's more, it has the largest z-score in the sample, which is not surprising because 615 is the largest value and therefore will be the farthest away from the mean. Why does this matter? Because most data, by observation and by assumption, follow a bell-shaped distribution, which is a symmetric distribution. We can then use the so-called empirical rule to determine how many data points, what percentage of the observations will be within a certain number less than or greater than the mean. We will cover this more fully in chapter 6. But for now, keep these three findings in mind. If data have a bell-shaped, then approximately 68% of the values of a normal random variable will be within plus or minus 1 standard deviation from the mean. Similarly, 95.44% will be within plus or minus 2 standard deviations from the mean, and 99.72% will be within plus or minus 3 standard deviations from the mean. This is also the illustration. As you will see, approximately 68% of the observations, that's the area under the curve and between 1 and minus 1 standard deviations. And this area will be between 2 and minus 2 standard deviations. And finally, all of this, which is 99.72%, will be between 3 and 3 standard deviations from the mean. Now remember extreme values? We also call them outliers. They are values that are extremely large or extremely small. So what we can already say here is if we have a data point and its z-score is less than minus 3 or greater than minus 3, then it's an outlier. Why do we say that? Let's go back to the graph. Look at this. If 99.7% of all observations are within 3 and minus 3 standard deviations, i.e. they have z-scores less than 3 and greater than minus 3, then if you have an observation whose z-score is like 5 or minus 7.2, then that means it's really very, very far to the left or very, very far to the right, i.e. they're greater than or smaller than 99.7% of the data, and therefore they're extreme observations. If you find outliers in your data, check carefully. It could be that the data was incorrectly recorded, a typographical error. Or it could be that the data value was incorrectly included. Or it could be that it really is correct and that there really is an extreme observation. That's the third possibility. Consider this again, the apartment rents. The lowest z-score is minus 1.2. The highest z-score is 2.27. 2.27 is less than 3, so it's not an outlier. Minus 1.2 is negative, but it's not as low as negative 3. Hence, it's also not an outlier.